purpose of this video is to introduce you to some low-hanging fruits of the completeness axiom. So this is section 2.4. It's titled applications of the supremum of the I'll call it the applications of the completeness axiom. That's how I'll call it. Okay, all right. So the first result, which is a really important result for us, is known as the Archimedean property. And to state the Archimedean property, if x and y are two real numbers, and let's say x is positive, then there exists a natural number. N such that n times x is greater than y. All right, so let's get started on the proof of the Archimedean property. So if let's suppose that y is less or equal to 0, then clearly, if y is less or equal to 0, then clearly the result is true for all natural numbers n. Right? Why? Because so clearly, if I take a natural number, it's positive, and I multiply that natural number by x, which is already set to be positive, then you get a positive number, which is going to be at least 0, right? So there's really nothing to prove here. The other intuitive understanding of the Archimedean property, which I almost forgot to say, is the following. The Archimedean property is telling you that if you give me two numbers, and let's say one of those numbers may be very, very small, and it's positive, and that's really all you need. The fact that it's positive means that you can find a natural number which is big enough, which is sufficiently large, so that once you multiply that natural number by x, which may be extremely small, you get something which is bigger than y, regardless of how big y is. That's possible, right? So in other words, you can fill the ocean with a spoon if you have enough time. Okay, all right, back to our proof. So the case where y is less or equal to 0 is clear. So let's assume that y is positive, and here we will use the method. We'll use the method of proof by contradiction. Okay, so today let me introduce an auxiliary set. Let A be the collection of all numbers of the type nx, such that n is some natural number. Okay, so in these sets, remember x is fixed, and I multiply x by all possible natural numbers, all of the natural numbers, and I get a bunch of numbers, and I put them in this set A. Then if the stated result is false, there does not exist some natural number n such that nx is greater than y. Right? And so if the result is false, then you cannot find a natural number such that nx is bigger than y. So then, in other words, to rephrase this, in other words, nx is less or equal to y for all natural number n. Okay, and now since the set A is not empty, why not? Well, you can pick n to be equal to 1, and if n is 1, then nx is x, and x of course is in the set, right? It's not empty. Little x is in the set. Then I don't want to use the word then here. We just say since A is not empty, by the completeness axiom, since A is bounded above, since A is bounded above by y, then it has a supremum. Okay, well, so I will let alpha be the supremum of the set A. Since x is positive, then you will agree that alpha minus x is less than alpha, right? So therefore, alpha minus x is not an upper bound, and that exists, since alpha minus x is not an upper bound, is less than alpha, and alpha is supposed to be the least upper bound, right? So alpha minus x cannot be an upper bound, and there exists an element, and there will exist an element of A, call it mx, such that alpha minus x is less than mx, right? So remember here, this means that by definition, because mx is in A, then m has to be a natural number, right? So you can find an element in the set A. Remember that A contains all numbers of the type nx, where n is a natural number. So you can find an element in the set which is bigger than alpha minus x. Okay, well then, so that being said, so as such, alpha must then be less than mx plus x, right? So solving the previous inequality for alpha gives us that, which, and then factoring x out, is m plus 1 times x. However, notice that m plus 1 times x is an element of A, since m is a natural number, and of course m plus 1 is a natural number, and the membership requirement of A is to be a natural number times x, and whatever this number is satisfies that criteria. So it's a member of A, and this clearly violates the fact that alpha is an upper bound of A, and therefore there exists a positive, there must exist a positive integer n, such that nx is greater than y. Okay, and this is the end of of the proof of the Archimedean property. All right, so so what is the use of this result, right? Let me show. So first, before I get into an example, let me provide you with a little bit of more insight behind the use of the Archimedean property. one way in which the Archimedean property is often used is as follows. Given any epsilon, which is a positive number, and think of epsilon as being a very, very small number, there exists a natural number n such that, by the Archimedean property, n times epsilon is bigger than 1, right? Because here, for me here, y is 1 and x is epsilon. And as a consequence, epsilon must then be bigger than 1 over n, and this is equivalent to 1 over n being less than epsilon. So in other words, we can find, so in fact, no matter how small epsilon is, we can find a natural number which is large enough to make 1 over n less than epsilon. So in other words, we can make 1 over n as small as desired, provided that n is sufficiently large. This is really important. We can make 1 over n as small as desired, provided that n is sufficiently large. Okay. All right. So more on the concrete stuff. I know you guys like concrete stuff, concrete examples, stuff that you can put your fingers on. Let's look at a concrete example. Let A be the set of all numbers of the type 1 over n, such that n is a natural number. And we want to prove that the infimum of A is a 0. Okay, so what is in this set? As an illustration, this is not a proof, but just to give you an idea behind what's about to happen. This set contains elements of the type 1, 1/2, 1/3, and so on, right? So you get a sequence of points essentially getting closer and closer and closer to 0. You never get quite to 0, but you get a sequence of points getting closer and closer to 0. And I claim that 0 is the greatest lower bound for these sets, right? That's what we really want to prove. Okay. So to prove this claim, we know that given an element of the set A, we can write A as 1 over k for some natural number k, right? Okay, and then since k is a natural number, then k must be greater or equal to 0, and of course this means that its reciprocal is also greater or equal to 0. Thus 0 must be less or equal to A, which is 1 over k for us here, for any A arbitrarily taken in the set A. This implies that 0 is a lower bound for A. Okay, so remember, to prove that 0 is the infimum of A, there are two things to prove from our previous section. First, we need to prove that 0 is a lower bound, and then we need to prove that 0 is the greatest lower bound. So that means that if I pick any number which is greater than 0, in other words, it's positive, it cannot be a lower bound for A. Okay, so let's make this happen. So for the second part, next, let's epsilon be a positive number. We need to prove that epsilon, as no matter how small epsilon is, cannot be a lower bound, right, for A. Okay, we need to establish this as transparently as possible, and this is where the Archimedean property is very handy. By the Archimedean property, we have that there exists a natural number n such that n times epsilon is bigger than 1, and this is equivalent to epsilon is greater than 1 over n, or 1 over n is less than epsilon, right? So you can find, so in other words, there exists an element A in the sets big A such that A is less than epsilon. So thus epsilon is not a lower bound for A, and we conclude that the infimum of A is equal to 0 because it is the greatest lower bound. Okay, so the next direct consequence of the completeness axiom is the density of the rationals. So theorem, the density of the rationals. Okay, all right, so again, let me state this result, and I'll give you a little bit of insight behind this theorem. The theorem is stated as follows: if x and y are two real numbers, and let's suppose x is less than y, then there exists a rational number. R such that x is less than r, which is less than y. Again, what are the implications of these results? Let me illustrate this a little bit. So suppose that you are on the real line. Okay, this is the real line, and you pick two real numbers. I'm not saying that they're rationals, just any two real numbers which are extremely close to each other. Well, the density of the rational tells you that inside this bubble, this blue bubble, you will find sitting in between these two numbers, you will find sitting a rational number. What is that? That's a number of the type m over n, where m and n are integers, and of course n is not 0. Okay, so no matter how small or how close, I would say, two real numbers are, there is a rational number, there is a ratio of 2, there is a number which can be written as a ratio of 2 integers, which is sitting in between these two. So the rationals are everywhere. They are dense. Okay, so as usual, we will try to prove this result to really understand why it is that this claim is true. Okay, so let me offer you a proof for the density of the rationals. Let us assume for now that x is greater or equal to 0. Okay, then since y minus x is positive, then by the Archimedean property, which we've seen earlier, there exists some natural number n such that n times y minus x is greater than 1, or in other words, n times y is greater than 1 plus nx. And because this is important and I want to come back to it, I will label this as star. And again, by the Archimedean property, the set, let me use call this here big X, which consists of numbers, natural numbers satisfying the condition natural numbers k such that k is bigger than nx, n times x. This set is not empty, right? Why? Because you can find a natural number which is bigger than nx. That's what the Archimedean property tells us. But the well-ordering principle, by the well-ordering principle, the set x is a subset of the natural numbers, right? And the well-ordering principle tells us that any subset of the natural numbers has a least element. Okay, so the set, any non-empty subset of the natural numbers has a least element. Okay, so the set x has a least element denoted by we'll call such an element little m. Furthermore, little m minus 1, okay, is not in the set, okay, because little m is the least element. So it must then be less or equal to nx, and nx is less than m because m is this is true because m is in x and m minus 1 is not in x. Okay, so therefore we then have that n times x is less than m, okay, coming from this here, which is less or equal to nx plus 1. If I add 1 to this, inequality, I get that m is less or equal to nx plus 1. And then by star, if you come back to star here, star, ooh, that sounds like a fancy name. All right. Okay, so nx plus 1 is less than ny. Okay, all right. So now dividing, now if we divide nx by n, so we get this, must then be less than m over n, which is then less than, right, ny over n. And this is equivalent to the fact that x is less than m over n, which is less than y. Okay. All right. So then this gives us exactly what we want. So the result is true because m over n, m is a natural number, n is a natural number, so m over n is a rational number, and we have just constructed a rational number which is sitting in between x and y. Okay. So moving forward, let us suppose next that x is less than 0 and somehow y is greater than 0. So you'll get a picture like this. This is not part of the proof, but it's just to build your intuition behind the argument which I'm about to make, right? So you have something like this, and clearly here, suppose next that, then we may pick our rational number r to be equal to 0, because 0 is sitting between x and y, since 0 is a rational number. Okay. All right. So finally, there's the last case, which is the following: if x is less than y, which is less than 0, then by multiplying this compound inequality by negative, we get that 0 is less than negative y, which is less than negative x. And using arguments similar, in fact identical to the previous case, we will so there exists a rational number q such that, because they're both positive, negative y and negative x are both positive, you can find a rational number sitting in between those two numbers. Next, multiplying this compound inequality by negative again, then we obtain that x is less than negative r, which is less than y, and of course negative r is a rational number. So we can also find a rational number sitting in between x and y if x and y are less than 0. And this completes the proof. We have exhausted all possibilities. Okay. All right. So, and the other remark that I would like to make, although I'm not going to dwell in this, because this can lead us astray and distract us from the fundamental concept that we are interested in. But it's worth noting that another consequence of the completeness axiom is the existence of nth root, and I will offer these results without any proof. I hope you can forgive that scene. For every real number, x which is positive, and every natural number n, there exists y which is positive, so that y power n is equal to x. That's an important result, but we will not prove that. But I just want you to be aware that it is a direct consequence of the completeness axiom as well. So the completeness axiom is in fact one of, in fact, is a central axiom for us in moving forward in advancing our study of the set of all real numbers. All right, so as another application of the completeness axiom, I claim that we can use the completeness axiom to prove that the set of all integers has no upper bound. Okay, so to this end, let us suppose by contradiction that z has an upper bound. Well, then since z is non-empty, by the completeness axiom, it has a least upper bound in the reals. So in other words, there exists some real number x such that x is the supremum of the integers. Okay, now since x minus 1 is less than x, then x minus 1 is not an upper bound. It's not an upper bound for z, right? Because x is the least upper bound. As such, there exists an integer k such that x minus 1 is less than k. Now adding 1 to on each side of the inequality x minus 1 is less than k yields that x must be less than k plus 1, which is an integer. So we have found an integer, namely k plus 1, which is larger than the supremum of the integers. And of course, this is absurd, right? So our assumption is false. So then, therefore, z is an unbounded subset of the reals. That's, again, there are many ways to prove this result, but this is one way of proving that z is an unbounded set by directly appealing to the completeness axiom. All right, so let's the next result that we will discuss is a corollary of the density of the rationals theorem. And let me state this this corollary. It says the following: given A and B, which are two real numbers with A less than B, there exists an irrational number T such that A is less than T, which is less than B. So in other words, it's not just that the rationals which are dense in the reals, the irrationals are also dense in the reals. Okay. So let's consider the real numbers. Let's say A minus square root of 2, and then and B minus square root of 2. And because A is less than B, then of course 1 minus square root of 2 is less than B minus square root of 2. Then by the density of the rational numbers, there exists a rational number R such that A minus square root of 2 is less than R, which is less than B minus square root of 2. And next we'll add square root of 2 to each side of the terms in the inequality star to obtain that A is less than R plus square root of 2, which is then less than B. And we claim here, I claim next that R plus square root of 2 is irrational in fact, otherwise if R plus square root of 2, if this is equal to S, which was a rational number, then square root of 2, which is S minus R, will have to be irrational since the sets of all rationals is closed under addition. In other words, if you add two rational numbers, you should subtract two rational numbers, you should get another rational number, right? So if you are to assume that S is irrational, and because R is rational, then S minus R will be a rational number, but S minus R is equal to square root of 2, and that's why we picked square root of 2. We could have picked square root of 3 or square root of 5 or 8 or pi, any other rational number for that matter, right? There's no square root of 2 here is not playing an essential role here. Okay, but the point is, R plus square root of 2 is an irrational number sitting in between A and B. Okay, and then so we get the desired result. Okay, thus the claim holds indeed. All right, so here's another exercise. Let A and B be two real numbers such that A is less than B. We want to prove that the open interval A and B intersect Q is an infinite set. Okay. All right. So here's the proof. So let us suppose by contradiction that A and B intersect Q is a finite set of, let's say, n distinct elements. Then we may write AB intersect Q. So in other words, there are finitely many rational numbers in between A and B. So we can write this as x1, x2, all the way till xn, because there are n many of them. And let us also we may also assume that we have ordered the element in the set such that x1 is less than x2, which is less than x3, and so on, which is less than xn. So x1 is the smallest and xn is the largest. Okay, so then now note that the set A x1 is an open sub interval, right, of A and B, and by the density of the rationals that exist, let's say xn plus 1, which is a rational number, and xn plus 1 is inside this set. So A and B intersect Q now can then be contains n plus 1 many rational numbers, and this is in contradiction to our assumption. So we have violated our own assumption, which shows that this assumption is false. So there, in fact, there are infinitely many rational numbers inside any open subset of the real numbers.